previous, do you have my voice and my screen? In previous meeting, we talked about this the language approach or their problem or their approach to solve ordinary differential equation. Uh, then we have solved uh, this via MATLAB program. Today we are going to study another Runge-Kutta methods, for example, fifth order. So, Runge-Kutta method in general, we have a variety of approach to solve the Runge-Kutta method. Uh, Another one is the fifth order Runge-Kutta method or Runge-Kutta-Fehlberg method, which we use the other more steps to solve the differential equation numerically. For example, uh, the algorithm for Runge-Kutta-Fehlberg method we have here. We have a differential equation, for example, y prime equals fxy, and sequence of yxn equals yn. To compute y in the next step, yxn plus 1, for example, we use these steps to solve or find the value of y in the next step, or as the xn plus h. Here, the index of x is n, which is a mistake. You should be aware of. X index n plus h is x n plus 1. We have numbers of k according to this formula. K1 equals steps h multiplied by f xn by n, k2 h multiplied by f at the point between xn yn and xn yn plus 1, xn plus 1 and yn plus 1. For example, this point xn plus h divided by 4 and yn plus k1 divided by 4. We can use k3, k4, k5 and k6 to obtain these values according to given formulas. This formula is difficult to memorize, but you can use this in mathematical, computer programming to further improve the accuracy of the solution. For example, in this case we use 6 number of k's, and we have y hat plus y hat n plus 1 is another Runge-Kutta method with yellow bar error OH4, and yn plus 1 as the Runge-Kutta-Fehlberg method you can see here these two different methods of evaluating differential equation or the solution of differential equation. These two different methods use same case K1, K3, and K4 and K5, but the Fehlberg, Rangikuta-Fehlberg approach use K6 and in addition to the other case used in the y hat n plus 1. The y hat n plus 1, we have the global error of or error about the when we use numbers of steps taken in the number of steps of OH4, and the next one yn plus 1. We have used this approach with the global error of OH5, and the Rangikuta-Fehlberg approach we can see improve the accuracy because we have less global. We have a global error of higher order, which means it's quite accurate when compared to the previous line or previous algorithm or y hat. Here we have a formula for the errors. The big E equals this rather complicated formula. Let me Assalamu alaikum. Salam. Yn plus 1, but of different orders of errors. We have yn and y hat n. Thus, instead of comparing estimates of yn plus 1 for h and half of h, we compared the estimates with y hat and yn plus 1 using fourth and fifth order global Runge-Kutta formulas. Both equations, as I mentioned, use the same case, but the last one used one case in addition, for example, K6. We have an example which we actually have this example in the previous meeting for previous approaches. We must solve y divided by dx equals minus 2x minus y with the initial conditions of y0 equals minus 1. Steps here we used 4.1 using the Runge-Kutta-Fehlberg methods. We get these values for the y in the next step. At the step 0 we have minus 1 for y, as you can see here, and the value for y hat according to the given formula we have uh, talked about is, you can see here, and the value for y index 1 is here, and the error for the y1, not the y hat, is this value, very close to 0. The exact value at the point 4.1 is minus 4.9145, and you can see another digits of that. And when you compare that with this y hat one, you can see uh, we have less error. We have much error when we compare that with the value of y1. The reason for the improvement of y1 compared to y hat 1 is that we have used an addition k6 in this formula. You can see here in y hat formula in the first line of this presenting, and the second one yn plus 1. You can see we have another k6 in this, which actually interpolate the function or the solutions of this differential equation with more accurate polynomials of higher degree, and we have a third much more accurate solution for y1. You can very easily code or program these algorithms. It is an iterative algorithms. All of these formulas are defined just for single step, and the other one will be repeated automatically by a computer, and you get much more and better accurate solutions. And the main objective and goal of this course is also to teach for you to learn how to use these methods in computer, because you know that computing this by hand is impossible, and the only way is to using this in software like MATLAB or Python or another software which you can use that. Solving by software is very easily, and you can use this in your future master thesis for your thesis. Here, the book says we would use the more accurate yn plus 1 for the next step. This algorithm is well documented and implemented in the Fortran program. You know, Fortran in the past was a software language for a computer language for scientific computing, but now it's outdated, and the new software computing like MATLAB and Python and Julia has have much more easily and much more accurate than Fortran with the much more libraries in this case and for using for scientific computing, especially numerical solutions or numerical solutions for differential equations. And these programs like MATLAB and Python, which much richer in the libraries, which uh, is available for the researchers and for the students and for those who related to industries in this case to use when compared to Fortran. And now the Fortran is outdated software and mm, no longer is used for scientific computing uh, today. You can see the difference or comparisons of numerical methods we have studied for solving the differential equations. For example, y prime equals f at the point x and y. You can see that in the table 6.5 here. We have studied the different approaches and methods which listed in the first column of this table, table 6.5, the Euler, uh, modified Euler, midpoint, Runge-Kutta of the fourth order, and Runge-Kutta, the last one, the Hilbert. And you can see in the third and the fourth columns of this table the accuracy of these approaches in the uh, listed format, and you can easily compare the efficiency and the accuracy of these different approaches. For example, the Euler, we have the global error of OH and the local error for the first or single step. The local error, as I mentioned in previous meeting, related to the error for just single step. For example, when you evaluate the value of y1 from y0, yeah, you have a local error. Global error, when you repeated this for multiple steps, y1, y2, y index 3, and vice versa, we have a global error. Uh, Actually, it's obvious that the global error is less accurate than local error. For example, OH, we have local error OH2 for Euler methods, which is obvious. In the second approach, we have second and the third approach, we have the solutions with the accuracy of H2, OH2, and OH3 for global and local errors respectively. And in Runge-Kutta fourth order, you can see the accuracy has improved far more. Furthermore, when compared to the midpoint and modified Euler, uh, finally we have a Runge-Kutta-Hilbert method which you can see very complex and much more complicated when compared to Ranjikuta of the fourth order, or in the compared to the Euler one, but we get more accurate solutions of OH5, the global error, and local error of OH6, which is OH6, for example, tells us that this solution is accurate for the polynomials of degree 6 at most to degree 6. When you compare that to the Euler one, for example, which tells us that this is accurate for the polynomials of degree 2 or 1, that is much more accurate and precise evaluation. If you have any uncertainty or question in this case, you can ask me any questions. Let me. We have another table, for example, following the table 6.5. For the step size of H 0.2, and in this case we use we compute the errors computes in different points, and we can see what happens in the next table, the first table for different age, the errors compared between the different methods, the Euler one, the modified Euler, they are in the good of the fourth order, and the different error. The Euler, we have different the values of error. Modified Euler is 2.11 e or multiplied by 10 powered with -1 is 10 minus 2, and different approaches at different steps by 0.4, 0.2, 0.1. We use a backward solution, backward solutions, and forward solution for that. We can see that errors related to the different Euler, modified Euler, and as we can expect here, the Euler method, we have used the accuracy of degree OH, or the first degree, and the degree for the polynomials of the first degree OH2 related to the polynomials of degree at most 2. We have another method of Runge-Kutta family methods. Here it's called Runge-Kutta-Mersenne method. The Runge-Kutta-Mersenne method, we compute the values of k, for example, for the 5 k's, k1 as the last k, as same as the k in the last formulas. Here k2, k3, k4, and we can see in general there is a similarity and difference between that and these Runge-Kutta formulations for the fourth order and the fifth order. The local error here is of the O degree of H5, more accurate than the fourth and less accurate than the Runge-Kutta-Verhelber's approach. Here, let me show you how we can solve this using MATLAB software. Let me open new scripts in MATLAB, and I can. The last one was UMI. Let me copy this. And here it's similar to the previous one, but we need to edit some of these formulas. We have a K1, Fx1, Y1, K2, H, F, H divided by 3, K1 divided by 3. Here, H divided by 3. Here we must use 1 divided by 3 and 1 divided by 3. The next k, we have a k index 3, k1, k2, k3. H3, K1 divided by 6, K2 divided by 6. H3, F, X1. Divided by 6, K2, and the same. K1. K4, H divided by 2, H quantitative method. This h divided by 2 k1 by 8 and 3 k3 h k1 by 8. We use this formula. Three eight k3. 3 8 k multiplied by k3 by 1. And we have another k5 equals h multiplied by 8 I comma yi. Let me x a plus h plus h y I plus k1 divided by 2 k1 k3 minus 3 divided by 2 multiplied by k3 plus 2 k4 plus 2 multiplied by k4. We have the y n plus 1 equals yn plus k1 plus 4k4 plus k5 divided by 6. 1 by 1 6 k1 4 k4. Here we have 4 k4 and k5. K5. The value of errors we can see here. The value of error is local error. We say local error equals 1/3. Let me I want 1/3 of class multiplied by 2k1 2k1 minus 9k3 plus 8k4 minus k5. K4 minus k5. 8 multiplied by k4. We run this. Let me hope you can see the values. We have a local error for each step. H is 4.1 and the value of y is for different steps. I don't know, Range-Kuta Merson method. We have this formula. Any questions? Let me. Once a very popular Range-Kuta method in the past was very popular, and it showed very accurate results. Also, uh, software like MATLAB or yeah, let's see, Maple also have an option for solving differential equations using Range-Kuta methods. For example, we can see this. Here is the MATLAB solution to our sample problem using its OD for part command, solving differential equation which use RKF. I think was the Range-Kuta Fehrenberg approach. For this command, but you can easily code these programs yourself, not using the MATLAB libraries. You can type this yourself. It's very simple. Just you need to know some initial concepts of MATLAB, like for loop and the arrays, the vectors in MATLAB. You can see the values in the book, the solutions of that 8464 as we computed here in this MATLAB. And the rank Guta method is efficient but simple method with a higher degree of accuracy when compared to other initial methods. Uh, Each kind of method we find the values of y or values of differential equations for solution of that. At the different steps after steps, we compute the value of y completely depending on the last step, uh, and obviously it uses less information of the steps, not just the last one, the steps before, and maybe the step uh, after that. And to remedy this drawback, uh, there is a multi-step method proposed by researchers to further prove the accuracy and uh, address the drawbacks or limitations of previous approaches. Uh, for example, the book says Rangikuta type methods, which include Euler and modified Euler as special cases, are called single-step methods because they use only the information from the last step computed. In this, they have the ability to perform the next step with the different step size and are ideal for beginning the solution where only initial conditions are available. After the solution has begun, however, there is additional information available about the functions. For example, we have its derivatives. And if we are wise enough to retain it in the memory of computer, a multi-step method is one that takes advantage of this fact. Uh, for example, if you remember in numerical in the previous course, numerical approaches for solving uh, for finding integrations numerically, uh, the Romberg's approach used the same idea as the multi-step approach of trapezoidal and with different steps. And here, this book, in this chapter, we are going to use the same idea in this regard. And the principle behind the multi-step approach is to use or utilize the past value of y and derivative, for example, y prime, to construct or interpolate a polynomial that approximate the derivative function. We can also extrapolate or predict the value of function in the next step based on the previous steps, not just the last one. Uh, there is a Adams method which used this idea to find values of previous steps, uh, values of the next step based on uh, several information of several previous steps. To derive the relation for the Adams method, we write the differential equation dy divided by dx equals fxy. In the form we have y prime is equal f, or instead dy, the differential of y with respect to the x, equals fxy. In the form dy equals fxy or y prime dx. By taking the integration between two consecutive points x1 and xn plus 1, from these both sides of this equation, we get this formula. The following box you can see in the bottom of the screen. When we take a differentiation integration from the left side, dy between xn to xn plus 1, we get yn plus 1 minus yn. That's obvious. The value of y at the endpoint minus the value of y at the xn, which is called yn plus 1 and yn. And taking the integration from the right side of this equation, which I highlighted with the blue color, is here the integration integrals from xn to xn plus 1 f at the point xy dx. We have this formula, and we want to use this formula to obtain the Adams approach. To integrate the term on the right, we approximate fxy as polynomials in x, deriving this by making it fit at the several past points. We interpret it based on the several past points, and we use 3 past points. For example, if we use 3 past points, the approximating polynomial would be quadratic, or of the degree 4 and degree 2. If we use 4 points, it will be a cubic. The more points we use, the better the accuracy we get. As we mentioned in previous course of numerical analysis, interpolating polynomials use this formula, which gets us quadratic approximations of f as a differential or y prime, or dy divided by dx. Here it uses the mathematical software to find these interpolations, but the formulation we use to approximate the value of f is here, and we get the same y integration, yn plus 1 minus yn, we get h divided by 12, 23 fn minus 16 fn minus 1 plus 5 fn minus 2, which is displayed in this box as the 6.14 formula, with the accuracy of degree O H4, which is which tells us the local error is uh, accurate or exact for polynomials of the degree up to 4 of the degree 4. We can use this equation 6.14 in this box. In this example, for the differential equations of dx divided by dy divided by dx minus 2x minus y with this initial condition and computed the values for y at the point 0.2 and 0.4 by using single step method. Uh, we studied different single step methods: Euler, modified Euler, and midpoint, Runge-Kutta, and Runge-Kutta-Fehlberg. Here it uses a Runge-Kutta-Fehlberg method with the step size of h equals 4.2, and we get the value for y at the next point after the 0.4 based on this value of h and this value y based on the 6.14 equation uh, gives us this value for the y at the point 0.6 minus 0.84 5008. When I compare that with this value y, uh, this is was with this h of 4.1. We solved this with MATLAB at the y1, y1, y2, 8.64, for example. I think, let me h is, yes, from I to 6 at this point 8.4. Comparing this result with the exact solution, we find the computed value has the error of 0.00138. We can reduce the size of error by doing the calculation with the smaller step size of 0.1. We use the fifth order value of Runge-Kutta-Fehlberg methods once again, and we get this value, which is quite close to the value we computed here, minus 8464 minus 0.8463, and the values of error is very close to 0, as you can see this number highlighted by blue color. This approach uses a multi-step approach. You can observe this approach is simple, efficient, but less accurate than the Runge-Kutta-Fehlberg or other Runge-Kutta methods, but computation is much more simple, and we can observe much more, much less complexity when we use the formula in this box, for example, compared to other methods. Any questions about this approach? We can use the same idea of Adam's formula to obtain efficient, more accurate, efficient algorithm. Assalamu alaikum. The last equation, for example, 6.14, use the value of Assalamu alaikum. For 3 point xn, xn minus 1, and xn minus 2, we use the informations of the y at the last 3 points, x1, xn minus 1, and xn minus 2. To estimate the next y for yn plus 1, we use the 3 point. If we're using 4 pass point, it is equivalent to integrating a cubic interpolating polynomial through 4 pass points, and we can get the values here. And we can let the integrations of f between xn to xn plus 1 as this formula of 4 point n minus 3, n minus 2, n minus 1, and at the point n with these weights C0, C1, C2, and C3, we suppose that this integration can be solved numerically with this the formula, the right side formula of this equation. You can see this is the assumption. We assume that this has the this simple structure, and let us examine how that will work with 4 constant or 4 weighted approach. The next formula is the same as this formula, but by shifting the origin to point to 0 from xn to 0, and taking integration between xn to xn plus 1, we simply get this formula from 0 to h fx dx equals this formula c0 f minus 3h, c1 f minus 2h, c2 f minus h, and c3 f at the origins or at the 0. We can use this integration right here in this formula. This is our integration, and we can get y as integrating of f with respect to x to x. This is by carrying this formula. For example, if we replace the f with h3, the integration became h4 divided by 4. We replaced the h with h3, and we get these equations. h4 divided by 4 equals c0 minus 3h3 plus c1 minus 2h3, and this gets us an equations. If we replace the function f with the h2, the analytical solutions of the left side of this equation, let's do h3 divided by 3, and the right side became c0 minus 3h2, c1 minus 2h2, and as follows. As you can see, if we replace the f integral by h, the analytical integrations of the 0 to h f dx became h2 divided by 2. You can see as the last equation in this screen, and the right side one just substituting the values of h with of f with the h, fx with x, f minus 3h, we get minus 3h, f minus 2h is equals minus 2h, and as the previous one, the next one became f. We replace the values of f with 1, just 1. The integrations of 0 to h 1 dx became h, as you can see in the last formula in this screen. H equals c0 at the constant functions of 1, c1 1, c2 1, and c3. And here we have 4 equations and 4 unknowns, c0, c1, c2, c3, and we can derive the values of constants c0, c1, c2, and c3 from this system of equations. The linear system we are to solve is this. This is equals the last systems, but in the matrix symbol or in matrix formulations, by dividing each side of these equations, for example, by or letting them by h1. If we let the values of h as a 1, we get these values. these equations, and the solution. We don't need to solve this system of equation because this system is uh, solved by researchers, and the solution is quite available to us. And C0 equals minus 9 divided by 24, C1 37 on 24, C2 minus 59 divided by 24, and C3 as you can see in this screen. This is values. This values is obtained using, you can solve this very easily in MATLAB or other software, but the one thing important for us is these values, not just solving them. And we get for the Adams formula according to this solution as this formulation in this box. Yn plus 1 equals Yn plus h divided by 24, 55 Fn minus 59 Fn minus 1 plus 37 Fn minus 2 minus 9 Fn minus 3 with the accuracy which is exact and accurate for polynomials of degree 5 or less. This is a local formula, and the accuracy or the error terms OH5 here is the local error. Any question in this case? If you have any question, you can ask me. I'm more than happy to answer you. Any question? But let me give you 15-minute rest because now is the Ramadan month, and I congratulate for all of you students, dear students, this holy month, and I hope and wish the best for you in this month. From Allah subhanahu wa ta'ala. And now you have 15 minutes approach for the solving the differential equation using the formula in this box. 6.15 Yn plus 1 equals Yn plus h divided by 24. 55 Fn minus 59 F index n minus 1 plus 37. These coefficients are obtained according to solving this system of linear equation. You can use them and memorize these coefficients in calculator and use them wherever we need. Let me talk about the next method which use similar approach but in advanced manner, in more sophisticated manner. Then I'm going to show or solve this formula by MATLAB for you. And you will see how easy using this formula in computer coding in MATLAB or maybe another software. The next approach is Adams-Moulton method, which is the improvement of the previous Adams method. It uses different approach, a different idea. At first, we used the previous Adams approach as a predictor formula, and by applying another formula, another similar formula called corrector formula, which corrects the previous one to improve the accuracy of the solution. It says it uses Adams method as a predictor formula, then applies a corrector formula based on constructing another cubic interpolating formula through 4 points. The one obtained with the formula, predictor formula, and 3 previously computed one. Let us see the predictor, which equals to the previous one. Yn plus 1 equals Yn plus h 24th of the parenthesis 55 Fn, 59 Fn minus 1, 37 F minus 2 minus 9 Fn minus 3. It uses the information of the last 4 steps to obtain the next step. Here we have Fn minus 3, Fn minus 2, Fn minus 1, and F and this n. And let me show you the character formula. This is another cubic interpolation of function f, which is Yn plus 1 equals Yn h divided by 24, 9 Fn plus 1, 19 F, and this in this x, n, and if minus 5 Fn minus 1 plus Fn minus 2. The difference between this and the previous, the character and the previous formula as a predictor, is that we use the information of the predictor to obtain the value of f index n plus 1, which is used in the character formula. We don't have the Fn plus 1 at the first, and to obtain this we solve this equation. We get Yn plus 1 by using Yn plus 1 and Xn plus 1 and putting them in the f of function f of x and y. We get the Fn plus 1. We illustrate the Adams-Moulton method using our earlier example. Dy dx equals minus 2x minus y. with this initial condition, the same example of the previous approaches. By using the predictor formula, we get y at the point 0.4 as this value. And we want to use the corrector formula to obtain a better solution. We need fn plus 1, as you can see in the 6.17 formula in this box. To obtain n f index n plus 1, we use the value of y at the 0.4 and the x, which is actually 0.4, to obtain the f at this value, which is fn plus 1, and we get fn plus 1 at this value, and by use this in the correction formula, we get this value. If you have any question regarding these two formula, you can ask me. And otherwise, I'm going to show you how can code this in MATLAB software. Let me obtain a new script. We want to use the predictor formula. The formula is predictor yn plus 1 equals yn p is index n plus 1 equals y parentheses or in the MATLAB we use Victor. We use a Victor y index, and here is formulated as y parentheses n plus h divided by 24 multiplied 55 fn 55 f and comma yn. F here is a differential function. F and is function of x and y minus 59 fn minus 1 xn minus 1 yn minus 1 plus 37 fn minus 2 37 minus 2 by n minus 2 minus 9 fn minus 3. We use the character. Let me copy and then paste and then edit the character. Formula yn is 24 9 19 here 9 n plus 1 by n plus 1 and minus plus 19 minus 5. Let me share that after this. The last video 9 minus 5 minus 5 n plus 1 n minus 1 and n plus 1 and n minus 1 and then minus 2. We use y2 and y3 from previous solving by 0 by 4 مساوي 3 3 x مساوي 4 let me run this code. Before we run, we want to save this code in document MATLAB and patterns. There is error here to code analysis valid file name. Let's in that rename non-count. There is must either real or positive integer. We have errors here. By wait, five. 0 here. 2, 2, 5, 4, 4 actually equals 4. The solutions of Adam Moulton's for y at the point, let me see, y0, by taking minus 8109 and minus 8109. Minus 8110. This value obtained by Adams Moulton approach. It's quite accurate because when we round off this number, we get minus 8110 for 4-digit meaningful digits here. You can see the whole code here. This is the initial points, and this we have a for loop and the predictor formula, the corrector, and just that. The last y is to print the y in the output. Here we can get two other values, for example y at the 0.5 and 0.6, as you can see here. The predicted formula, the analytical formula, are shown in table 6.10. The value of x 0.1, 0.2, 0.3, 0.4, 0.5, and the value of y as the solution. fxy is minus 2x minus y, which is the formula for dx dy divided by dx or y prime. We need these values if you want to show, for example, fx. For example, let me show f x 4 x 5 y 5, and type that here, and here is 4. The indices in MATLAB indexes are starting from 1, but this book The indexes are starting from 0. Let me run that and show the output. This is the value of f. You can see here 22, 24, 22, 25. It is a rounded or in فارسی بسید مقدار گرد شده a rounded value for f. It's all about how we can code in the MATLAB as an efficient software to solve numerical problems or numerical solutions of differential equations or other equations related to differential for engineering and other branch of science. The next subject of this meeting is about changing the step size. In previous formulas, we use the same step size at 0.1 or 0.2. Here, when we change the step size, we can get more efficient algorithm. We may, and first stage, use the step size from 0.2, and in the next stage, use another step size and get different values for y, and using this information to improve the value of y. The book says when the predicted and corrected value agrees to as many decimals as desired accuracy, we can save computational effort by increasing the step size. For example, here in previous equations, we get the value of predictor at the point 0.4 minus 0.8109. We have accuracy for the same digits for the first 5 meaningful digits in these two values. If these errors of, I can see very small errors related in these both formulas. When we are satisfied with this accuracy, we can get we can use bigger step to find the same accurate solution. The book says we can conveniently double the step size after we have 7 equispaced values by omitting every second one. Then the difference between the predicted and corrected values reaches or exceeds the accuracy criterion, we should decrease the step size. If we interpolate two additional y values with the fourth degree polynomial, where the error will be of OH5. Here we can see y index n-1 divided by 2 and yn minus 3 divided by 2, and the predictor one is 1 divided by 128, 35 by n, 140 by n minus 1, and these values. When we use the h as a 3, as a 2, we get 1 divided by 25 minus 5 by n minus 60 by n minus 1 as the correct one. Use of these values with yn and yn minus 1 gives 4 values of functions at the interval of this dx or half of dh. And we can see that we quite easily get efficient but much faster algorithm than this one. The efficiency of Adams-Moulton is about twice of Runge-Kutta, Fehlberg, and Runge-Kutta methods. But the means of efficiency here, there is a difference between the efficiency and accuracy. Accuracy means how exact our solution is. How exact our solution is the definitions of accuracy. But the efficiency means how fast, how quick our algorithm is. If the speed of our algorithm is high, our algorithm is much efficient than a low speed algorithm. But the important factor that must be taken into consideration is accuracy. When you decrease the accuracy, you increase the efficiency, and vice versa. An important concept is how to find or to compromise or find a trade-off between these two opposing objectives. Two opposing objectives. One is increasing efficiency, and other is increasing accuracy. Then the efficiency of Adams-Moulton is twice that of Runge-Kutta. It means that the Adams algorithms is twice faster than Runge-Kutta algorithms, but it may get us a less accurate solution. But in the case of when we satisfied with less accurate solution, it is important to use a much more efficient algorithm. When we use this kind of algorithms to find the solution for thousands of steps, it is important to take the efficiency into consideration. Otherwise, it is important to take the accuracy into consideration. Any questions here? You can ask me. Only two functions evaluation are needed per step for the former method. For example, here refers to Adams-Moulton. Where 6 or 4 are required with the single step alternative in the later method, which is Runge-Kutta-Fehlberg approach. But they all have the similar error terms. This is the end of this Adams kind of multiple size approach. Here we have studied different approaches for solving ordinary differential equations of uh, degree 1. We used Euler, modified Euler methods, midpoint, Runge-Kutta of 4th order, Runge-Kutta of 5, Runge-Kutta of Fehlberg, and Adams-Moulton algorithms. And as you can see, these approaches are easily to code in computer. The next subject that I want to talk about is stability consideration. Stability consideration is a concept of different of seeing or taking a differential equation or solutions of differential equation from different viewpoints about how the error propagated from the one step until the next step. You know, we inherit error at the n+1 step from the last step. In numerical solution or numerical approach, it's obvious that we have error. As you mentioned, you observe in numerical algorithms, and we start from a point and find the value of y in the next point and the next point, and continue that and hundreds and thousands times to reach the last point, and we get a value of y in number of points, not in all of the intervals for example, between A and B. We find in the finite number in this intervals, and an obvious observation is error. And an important concept that we should take into account or take into consideration is how the errors propagated or transferred from one step to the next step, or how the error at the current step lead to errors in the future step in finding the solution. And if this amount of error became infinite in many big iterations or many big steps or thousands of steps, we can say that this algorithm is stable, and otherwise the algorithm is unstable because the errors become bigger and bigger, and we no longer can rely on the values of y computed by unstable algorithm when our iteration are high, or we use thousands of iteration. In this case, the solution is no longer reliable. In getting the solution to a differential equation, one must always worry whether the method is stable. In a stable method, early errors due to imprecision of a method or to an initial value that is slightly incorrect are damped out as the computations proceed or continue. They do not grow without bound. The opposite is true for an unstable method. When the errors grow or increase without bound, in this case, the algorithm or the approach is unstable. If the errors increase or bounded to up to some values, we say that this algorithm is stable, and a stable algorithm is a kind of algorithm we can rely on in our computation, for example, in science or in engineering or in economy or other branch of science. Uh, The book says the discussion of Euler method in section 6.2, we showed the condition for stability. This was not a simple task, but it is easier to see if a method is stable or unstable by testing it with certain kinds of derivative functions. Y prime is equals fxy. Consider the differential equation we have here. dy divided by dx equals fxy equals minus 2y plus 2 with this initial condition. If you solve this equation by analytical methods, you get this value as the value. The analytical method is always accurate, but the numerical one is inaccurate. But the problem is the analytical solution is not available in many cases, in many differential equations related to science, technology, and other area. Um, and the curve for y-axis is smooth, which means it's differentiable from for different orders. By starting at the initial value y equals -1 at the initial point and continuing rapidly upward with the slope of 4, which is the slope of y is at the initial point at the 0, and became y prime is equals 4. The differentiation of y at the initial point is 4, but we proceed, the value of y is increasing with this slope. Crossing the x-axis at about this point, this is our zero function and approaching the asymptotic of y equals 1 as x increases by x3, the y value is within 15% of its limiting value. Uh, and we use this formula yn plus 1 equals yn minus 1 plus 2h f x index n by index n. Our step size is 2h, which has the permutation values of that value h3 o h3 smaller than for simple Euler method, which is of OH2. Here is OH3, particularly with the small values for H. If we apply this equation 6.18, to this differential equation, this initial value with the h value or step size of 0.1, we get the results in table 6.11. We need a starting value at x0 with this. There were from the given y0 is minus 1 and analytical value is x equals 0.1. We get this. You can see the value of errors, the computed value of y, the analytical value of y or exact value, the error and relative error. The error, as we get away from the initial point, we get higher and higher errors. For example, at the point 4, we have near 3 values for errors, and this is the relative error. This is resulted from these equations. This table shows the results from the simple Euler method. We take a look at error and relative errors. When we go away from the initial point, we get the very few amount of error and few amount of relative error. This is the simple Euler method is a stable method, and this 6.18 approach is unstable method, which has a higher and higher amount of error, and observe in table 6.11 that we get good results up to about this point. But from x2, the computed values are increasingly poor, and as x approaches 4, they are completely useless or inappropriate. They oscillate widely about the symptotic value for y. Compare this with the result from a simple computation, Euler computation, also with same step size. that are given in the table 6.12. There are much less accurate at a small value of x, magnitudes of the error from the simple Euler computation between this and these are on the average nearly 20 times as large at this value. For example, the next one, we have this amount of errors, minus 0.431. When we compare to that, the first approach is uh, much accurate at the first, the second, the third, and the fifth algorithm per step. But the point is that this algorithm is unstable, and that one is let me uh, ask your questions if you have any questions, or let me uh, finish this class because now is the Ramadan month, and I want to take it into considerations. And our class become inefficient if we continue until the last minute. If you have any questions, you can ask me. I'm uh, here for you. On computer yourself. Actually, you have a project from the previous meeting. I speak the time to send me your project, and if I don't mistake, the next meeting I will have another project for you, but this meeting is on yourself to examine these approaches and study these approaches. These are simple approaches, not difficult if you study one. Uses the very simple ideas, and I hope and wish for you, dear students, the best. Thank you very much.
Thank you, Doctor.